Chapter 9 Soaring Weather Introduction Glider Pilots face a multitude of decisions, starting with the decision to take to the air. Pilots must determine if weather conditions are safe, and if current conditions support a soaring flight. Gliders, being powered by gravity, are always sinking through the air. Therefore, glider pilots must seek air that rises faster than the sink rate of the glider to enable prolonged flight. Glider pilots refer to rising air as lift, not to be confused with the lift created by the wing. The atmosphere. The atmosphere is a mixture of gases surrounding the Earth. Without it, there would be no weather, wind, clouds, precipitation, or protection from the sun's rays. Though this protective envelope is essential to life, it is extraordinarily thin. When compared to the radius of the Earth, 3,438 nautical miles, nm, the vertical limit of the atmosphere represents a very small distance. Although there is no specific upper limit to the atmosphere, it simply thins to a point where it fades away into space. The layers up to approximately 164,000 feet, about 27 nautical miles, contain 99.9% of atmospheric mass. At that altitude, the atmospheric density is approximately 1,000th the density of that at sea level. Figure 9.1, Composition. The Earth's atmosphere is composed of a mixture of gases, with small amounts of water, ice, and other particles. Two gases, nitrogen, N2, and oxygen, O2, comprise approximately 99% of the gaseous content of the atmosphere. The other 1% is composed of various trace gases. Nitrogen and oxygen are both considered permanent gases, meaning their proportions remain the same to approximately 260,000 feet. Water vapor, H2O, on the other hand, is considered a variable gas. Therefore, the amount of water in the atmosphere depends on the location and the source of the air. For example, the water vapor content over tropical areas and oceans accounts for as much as 4% of the gases displacing nitrogen and oxygen. Conversely, the atmosphere over deserts and at high altitudes exhibits less than 1% of the water vapor content. Figure 9.2. Although water vapor exists in the atmosphere in small amounts as compared to nitrogen and oxygen, it has a significant impact on the production of weather. This is because it exists in two other physical states, liquid, water, and solid, ice. These two states of water contribute to the formation of clouds, precipitation, fog, and icing, all of which are important to aviation weather. Properties. The state of the atmosphere is defined by fundamental variables, namely temperature, density, and pressure. These variables change over time and, combined with vertical and horizontal differences, lead to daily weather conditions. Temperature. The temperature of a gas is the measure of the average kinetic energy of the molecules of that gas. Fast-moving molecules are indicative of high kinetic energy and warmer temperatures. Conversely, slow-moving molecules reflect lower kinetic energy and lower temperatures. Air temperature is commonly thought of in terms of whether it feels hot or cold. For quantitative measurements, the Celsius, degrees Celsius, scale is used in aviation, although the Fahrenheit, degree Fahrenheit, scale is still used in some applications. Density. The density of any given gas is the total mass of molecules in a specified volume, expressed in units of mass per volume. Low air density means a smaller number of air molecules in a specified volume, while high air density means a greater number of air molecules in the same volume. Air density affects aircraft performance, as noted in Chapter 5, Glider Performance. Pressure. Molecules in a given volume of air not only possess a certain kinetic energy and density, but they also exert force. The force per unit area defines pressure. At the Earth's surface, the pressure exerted by the atmosphere is due to its weight. Therefore, pressure is measured in terms of weight per area. For example, atmospheric pressure is measured in pounds per inch 2, pound/in2. From the outer atmosphere to sea level, a typical value of atmospheric pressure is 14.7 pounds/in2. In aviation weather reports, the units of pressure are inches of mercury, Hg, and millibars, mb, and 29.92 Hg equals 1013.2 mb. This force or pressure is created by the moving molecules act equally in all directions when measured at a given point. In the meter report, see Figure 9.3, the local altimeter setting A2955, read is 29.55, is the pressure Hg. In the remarks, RMK, section of this report, sea level pressure expressed as SLPO10, the value expressed in millibars, HPA, is used in weather forecasting. Dry air behaves almost like an ideal gas, meaning it obeys the gas law given by P/dt equals R, where P is pressure, D is density, T is temperature, and R is a constant. This law states that the ratio of pressure to the product of density and temperature must always be the same. For instance, at a given pressure, if the temperature is much higher than standard, then the density must be much lower. Air pressure and temperature are usually measured, And using the gas law, density of the air can be calculated and used to determine aircraft performance under those conditions. Standard atmosphere. Using a representative vertical distribution of these variables, the standard atmosphere has been defined and is used for pressure altimeter calibrations. Since changes in the static pressure can affect pitot-static instrument operation, it is necessary to understand basic principles of the atmosphere. To provide a common reference for temperature and pressure, a definition for standard atmosphere, also called International Standard Atmosphere, ISA, has been established. In addition to affecting certain flight instruments, these standard conditions are the basis for most aircraft performance data. At sea level, the standard atmosphere consists of a barometric pressure of 29.92 Hg, or 1013.2 MB, and a temperature of 15 degrees Celsius or 59 degrees Fahrenheit. Under standard conditions, ISA, a column of air at sea level weighs 14.7 pounds/in2. Since temperature normally decreases with altitude, a standard lapse rate can be used to calculate temperature at various altitudes. Below 36,000 feet, the standard temperature lapse rate is 2 degrees Celsius, 3.5 degrees Fahrenheit, per 1,000 feet of altitude change. Pressure does not decrease linearly with altitude, but for the first 10,000 feet, 1 Hg for each 1,000 feet approximates the rate of pressure change. It is important to note that the standard lapse rates should be used only for flight planning purposes, with the understanding that large variations from standard conditions can exist in the atmosphere. Figure 9.4. Layers of the atmosphere. The Earth's atmosphere is divided into 5 strata, or layers: troposphere, stratosphere, mesosphere, thermosphere, and an exosphere. Figure 9.5. These layers are defined by the temperature change with increasing altitude. The lowest layer, called the troposphere, exhibits an average decrease in temperature from the Earth's surface to about 36,000 feet above mean sea level, MSL. The troposphere is deeper in the tropics and shallower in the polar regions. It also varies seasonally, being higher in the summer and lower in the winter months. Almost all of the Earth's weather occurs in the troposphere, as most of the water vapor and clouds are found in this layer. The lower part of the troposphere interacts with the land and sea surface, providing thermals, mountain waves, and sea breeze fronts. Although temperatures decrease as altitude increases in the troposphere, local areas of temperature increase, inversions, are common. The top of the troposphere is called the tropopause. The pressure at this level is only about 10% of MSL, 0.1 atmosphere, and density is decreased to about 25% of its sea level value. Temperature reaches its minimum value at the tropopause, approximately -55 degrees Celsius, -67 degrees Fahrenheit. For pilots, this is an important part of the atmosphere because it is associated with a variety of weather phenomena, such as thunderstorm tops, clear air turbulence, and jet streams. The vertical limit altitude of the tropopause varies with season and with latitude. The tropopause is lower in the winter and at the poles, it is higher in the summer and at the equator. The tropopause separates the troposphere from the stratosphere. In the stratosphere, the temperature tends to first change very slowly with increasing height. However, as altitude increases, the temperature increases to approximately 0 degrees Celsius, 32 degrees Fahrenheit, reaching its maximum value at about 160,000 feet MSL. Unlike the troposphere, in which the air moves freely both vertically and horizontally, the air within the stratosphere moves mostly horizontally. Gliders have reached into the lower stratosphere using mountain waves. At these altitudes, pressurization becomes an issue, as well as the more obvious breathing oxygen requirements. Layers above the stratosphere have some interesting features that are normally not of importance to glider pilots. However, interested pilots might refer to any general text on weather or meteorology. Scale of weather events. When preparing forecasts, meteorologists consider atmospheric circulation on many scales. To aid the forecasting of short and long-term weather, various weather events have been organized into 3 broad categories called the scales of circulations. The size and lifespan of the phenomena in each scale are roughly proportional, so that larger size scales coincide with longer lifetimes. The term microscale refers to features with spatial dimensions of 0.10 to 1 nautical mile and lasting for seconds to minutes. An example is an individual thermal. The term mesoscale refers to the horizontal dimensions of 1 to 1,000 nautical miles and lasting for many minutes to weeks. Examples include mountain waves, sea breeze fronts, thunderstorms, and fronts. Research scientists break down the mesoscale into further subdivisions to better classify various phenomena. The term macroscale refers to the horizontal dimensions greater than 1,000 nautical miles and lasting for weeks to months. These include the long waves in the general global circulation and the jet streams embedded within those waves. Figure 9.6. Smaller scale features are embedded in larger scale features. For instance, a microscale thermal may be just one of many in a mesoscale convergence line, like a sea breeze front. The sea breeze front may occur only under certain synoptic, i.e., simultaneous, conditions, which is controlled by the macroscale circulations. The scales interact, with feedback from smaller to larger scales and vice versa, in ways that are not yet fully understood by atmospheric scientists. Generally, the behavior and evolution of macroscale features are more predictable, with forecast skill decreasing as scale diminishes. For instance, forecasts of up to a few days for major events, such as a trough with an associated cold front, have become increasingly accurate. However, nobody would attempt to forecast the exact time and location of an individual thermal an hour ahead of time. Since most of the features of interest to soaring pilots lie in the smaller mesoscale and microscale range, prediction of soaring weather is a challenge. Soaring forecasts should begin with the macroscale, which identifies large-scale patterns that produce good soaring conditions. This varies from site to site and depends, for instance, on whether the goal is thermal, ridge, or wave soaring. Then, mesoscale features should be considered. This may include items such as the cloudiness and temperature structure of the air mass behind a cold front, as well as the amount of rain produced by the front. Understanding lift types, and environments in which they form, is the first step to understanding how to forecast soaring weather. Thermal soaring weather. A thermal is a rising mass of buoyant air. Thermals are the most common updraft used to sustain soaring flight. In the next sections, several topics related to thermal soaring weather are explored, including thermal structure, atmospheric stability, the use of atmospheric soundings, and air masses conducive to thermal soaring. Convection refers to an energy transfer involving mass motions. Thermals are convective currents and are one means by which the atmosphere transfers heat energy vertically. Advection is the term meteorologists use to describe horizontal transfer, for instance, cold air advection after the passage of a cold front. As a note of caution, meteorologists use the word convection to mean deep convection, that is, thunderstorms. Unfortunately, there is often a fine meteorological line between a warm, sunny day with plenty of thermals and a warm, sunny day that is stable and produces no thermals. To the earthbound general public, it matters little, either is a nice day. Glider pilots, however, need a better understanding of these conditions and must often rely on their own forecasting skills. Thermal shape and structure. Two primary conceptual models exist for the structure of thermals: bubble model and column or plume model. Which model best represents thermals encountered by glider pilots is a topic of ongoing debate among atmospheric scientists. In reality, thermals fitting both conceptual models likely exist. A blend of the models, such as individual strong bubbles rising within one plume, may be what occurs in many situations. These models attempt to simplify a complex and often turbulent phenomenon, so many exceptions and variations are to be expected while actually flying in thermals. Many books, articles, and internet resources are available for further reading on this subject. The bubble model describes an individual thermal resembling a vortex ring, with rising air in the middle and descending air on the sides. The air in the middle of the vortex ring rises faster than the entire thermal bubble. The model fits occasional reports from glider pilots. At times, one glider may find no lift, when only 200 feet below another glider climbs away. At other times, one glider may be at the top of the bubble climbing only slowly, while a lower glider climbs rapidly in the stronger part of the bubble below. Figure 9.7, more often, a glider flying below another glider circling in a thermal is able to contact the same thermal and climb, even if the gliders are displaced vertically by 1,000 feet or more. This suggests the column or plume model of thermals is more common. Figure 9.8, which of the two models best describes thermals depends on the source or reservoir of warm air near the surface. If the heated area is rather small, one single bubble may rise and take with it all the warm surface air. On the other hand, if a large area is heated and one spot acts as the initial trigger, surrounding warm air flows into the relative void left by the initial thermal. The inrushing warm air follows the same path, creating a thermal column or plume. Since all the warmed air near the surface is not likely to have the exact same temperature, it is easy to envision a column with a few or several embedded bubbles. Individual bubbles within a thermal plume may merge, while at other times, two adjacent and distinct bubbles seem to exist side by side. No two thermals are exactly alike since the thermal sources are not the same. Whether considered a bubble or column, the air in the middle of the thermal rises faster than the air near the sides of the thermal. A horizontal slice through an idealized thermal provides a bullseye pattern. Real thermals usually are not perfectly concentric. Techniques for best using thermals are discussed in the next chapter. Figure 9.9. The diameter of a typical thermal cross-section is on the order of 500 to 1,000 feet, though the size varies considerably. Typically, due to mixing with the surrounding air, thermals expand as they rise. Thus, the thermal column may actually resemble a cone, with the narrowest part near the ground. Thermal plumes also tilt in a steady wind, and can become quite distorted in the presence of vertical shear. If vertical shear is strong enough, thermals can become very turbulent or become completely broken apart. A schematic of a thermal life cycle in wind shear is shown in Figure 9.10. Atmospheric stability. Stability in the atmosphere tends to hinder vertical motion, while instability tends to promote vertical motion. A certain amount of instability is desirable for glider pilots. Without it, thermals would not develop. If the air is moist enough and the atmospheric instability is deep enough, thunderstorms and associated hazards can form. Thus, an understanding of atmospheric stability and its determination from available weather data is important for soaring flight and safety. As a note, the following discussion is concerned with vertical stability of the atmosphere. Other horizontal atmospheric instabilities, such as the evolution of large-scale cyclones, are not covered here. Generally, a stable dynamic system is one in which a displaced element returns to its original position. An unstable dynamic system is one in which a displaced element accelerates away from its original position. In a neutrally stable system, the displaced element neither returns to nor accelerates from its original position. In the atmosphere, it is easiest to use a parcel of air as the displaced element. The behavior of a stable or unstable system is analogous to aircraft stability discussed in Chapter 3, Aerodynamics of Flight. For simplicity, assume first that the air is completely dry. Effects of moisture and atmospheric stability are considered later. A parcel of dry air that is forced to rise expands due to decreasing pressure and cools in the process. By contrast, a parcel of dry air that is forced to descend is compressed due to increasing pressure and warms. If there is no transfer of heat between the surrounding, ambient air and the displaced parcel, the process is called adiabatic. Assuming adiabatic motion, a rising parcel cools at a lapse rate of 3 degrees Celsius, 5.4 degrees Fahrenheit, per 1,000 feet, known as the dry adiabatic lapse rate, DALR. The DALR is the rate at which the temperature of unsaturated air changes as a parcel ascends or descends through the atmosphere, which is approximately 9.8 degrees Celsius per 1 kilometer. On a thermodynamic chart, parcels cooling at the DALR are said to follow a dry adiabatic. A parcel warms at the DALR as it descends. In reality, heat transfer often occurs. For instance, as a thermal rises, the circulation in the thermal itself, recall the bubble model, mixes in surrounding air. Nonetheless, the DALR is a good approximation. The DALR represents the lapse rate of the atmosphere when it is neutrally stable. If the ambient lapse rate in some layer of air is less than the DALR, for instance, 1 degree Celsius per 1,000 feet, then that layer is stable. If the lapse rate is greater than the DALR, it is unstable. An unstable lapse rate usually occurs within a few hundred feet of the heated ground. When an unstable layer develops aloft, the air quickly mixes and reduces the lapse rate back to DALR. It is important to note that the DALR is not the same as the standard atmospheric lapse rate of 2 degrees Celsius per 1,000 feet. The standard atmosphere is a stable one. Another way to understand stability is to imagine two scenarios, each with a different temperature at 3,000 feet above ground level, AGL, but the same temperature at the surface, nominally 20 degrees Celsius. In both scenarios, a parcel of air that started at 20 degrees Celsius at the surface has cooled to 11 degrees Celsius by the time it has risen to 3,000 feet at the DALR. In the first scenario, the parcel is still warmer than the surrounding air, so it is unstable and the parcel keeps rising, a good thermal day. In the second scenario, the parcel is cooler than the surrounding air, so it is stable and sinks. The parcel in the second scenario would need to be forced to 3,000 feet AGL by a mechanism other than convection, such as being lifted up a mountainside or a front. Figure 9.11. Figure 9.11 also illustrates factors leading to instability. A stable atmosphere can turn unstable in one of two ways. First, if the surface parcel warms by more than 2 degrees Celsius, to greater than 22 degrees Celsius, the layer to 3,000 feet then becomes unstable in the second scenario. Thus, if the temperature of the air aloft remains the same, warming the lower layers causes instability and better thermal soaring. Second, if the air at 3,000 feet is cooler, as in the first scenario, the layer becomes unstable. Thus, if the temperature on the ground remains the same, cooling aloft causes instability and better thermal soaring. If the temperatures aloft and at the surface warm or cool by the same amount, then the stability of the layer remains unchanged. Finally, if the air aloft remains the same, but the surface air cools, for instance, due to a very shallow front, then the layer becomes even more stable. An inversion is a condition in which a layer warms as altitude increases. Inversions can occur at any altitude and vary in strength. In strong inversions, the temperature can rise as much as 10 degrees Celsius over just a few hundred feet of altitude gain. The most notable effect of an inversion is to cap any unstable layer below. Along with trapping haze or pollution below, it also effectively provides a cap to any thermal activity. So far, only completely dry air parcels have been considered. However, moisture in the form of water vapor is always present in the atmosphere. As a moist parcel of air rises, it cools at the dowler until it reaches its dew point, at which time the air in the parcel begins to condense. During the process of condensation, heat, referred to as latent heat, is released to the surrounding air. Once saturated, the parcel continues to cool, but since heat is now added, it cools at a rate lower than the dowler. The rate at which saturated air cools with height is known as the saturated adiabatic lapse rate, SALR. Unlike the dowler, the SALR varies substantially with altitude. At lower altitudes, it is on the order of 1.2 degrees Celsius per 1,000 feet, whereas at middle altitudes it increases to 2.2 degrees Celsius per 1,000 feet. Very high up, above approximately 30,000 feet, little water vapor exists to condense, and the SALR approaches the dowler. Air mass is conducive to thermal soaring generally. The best air masses for thermals are those with cool air aloft, with conditions dry enough to allow the sun's heating at the surface, but not dry enough that cumulus form. Along the west coast of the continental United States, these conditions are usually found after passage of a Pacific cold front. Similar conditions are found in the eastern and Midwest United States, except the source air for the cold front is from polar continental regions, such as the interior of Canada. In both cases, high pressure building into the region is favorable, since it is usually associated with an inversion aloft, which keeps cumulus from growing into rain showers or thundershowers. However, as the high pressure builds after the second or third day, the inversion has often lowered to the point that thermal soaring is poor or no longer possible. This can lead to warm and sunny, but very stable conditions, as the soaring pilot awaits the next cold front to destabilize the atmosphere. Fronts that arrive too close together can also cause poor post-frontal soaring, as high clouds from the next front keep the surface from warming enough. Very shallow cold fronts from the northeast, with cold air only 1,000 or 2,000 feet deep, often have a stabilizing effect along the plains directly east of the Rocky Mountains. This is due to cool low-level air undercutting warmer air aloft advecting from the west. In the desert southwest, the Great Basin, and Intermountain West, good summertime thermal soaring conditions are often produced by intense heating from below, even in the absence of cooling aloft. This dry air mass with continental origins produces cumulus bases 10,000 feet AGL or higher. At times, this air spreads into eastern New Mexico and western Texas as well. Later in the summer, however, some of these regions come under the influence of the North American monsoon, which can lead to widespread and daily late morning or early afternoon thundershowers. Figure 9.12, cloud streets. Cumulus clouds are often randomly distributed across the sky, especially over relatively flat terrain. Under the right conditions, however, cumulus can become aligned in long bands, called cloud streets. These are more or less regularly spaced bands of cumulus clouds. Individual streets can extend 50 miles or more, while an entire field of cumulus streets can extend hundreds of miles. The spacing between streets is typically 3 times the height of the clouds. Cloud streets are aligned parallel to the wind direction, thus, they are ideal for a downwind cross-country flight. Glider pilots can often fly many miles with little or no circling, sometimes achieving glide ratios far exceeding the still air value. Cloud streets usually occur over land with cold air outbreaks, for instance, following a cold front. Brisk surface winds and a wind direction remaining nearly constant up to cloud base are favorable cloud street conditions. Wind speed should increase by 10 to 20 knots between the surface and cloud base, with a maximum somewhere in the middle of or near the top of the convective layer. Thermals should be capped by a notable inversion or stable layer. A vertical slice through an idealized cloud street illustrates a distinct circulation, with updrafts under the clouds and downdrafts in between. Due to the circulation, sink between streets may be stronger than typically found away from cumulus. Figure 9.13, thermal streets, with a circulation like Figure 9.13, may exist without cumulus clouds. Without clouds as markers, use of such streets is more difficult. A glider pilot flying upwind or downwind in consistent sink should alter course crosswind to avoid inadvertently flying along a line of sink between thermal streets. Thermal waves. Figure 9.14 shows a wave-like form for the inversion capping the cumulus clouds. If the winds above the inversion are perpendicular to the cloud streets and increasing at 10 knots per 5,000 feet or more, cloud street waves can form in the stable air above. Though usually relatively weak, thermal waves can produce lift of 100 to 500 fpm and allow smooth flight along streets above the cloud base. Figure 9.14, so-called cumulus waves also exist. These are similar to cloud street waves, except that cumulus clouds are not organized in streets. Cumulus waves require a capping inversion or stable layer and increasing wind above cumulus clouds. However, directional shear is not necessary. Cumulus waves may also be short-lived, and difficult to work for any length of time. An exception is when the cumulus is anchored to some feature, such as a ridge line or short mountain range. In these cases, the possible influence of the ridge or mountain in creating the wave lift becomes uncertain. Further discussion of atmospheric waves appears later in this chapter. As a final note, thermal waves can also form without clouds present. Thunderstorms in unstable atmosphere can provide great conditions for thermal soaring. If the atmosphere is too moist and unstable, however, cumulonimbus, CB, or thunderclouds can form. CB clouds are the recognized standard marker of thunderstorms. When CB builds sufficiently, it changes from rainstorm to thunderstorm status. Well-developed CB clouds are thunderstorms. Not all precipitating, large cumuliform clouds are accompanied by lightning and thunder, although their presence is usually an indication that conditions are ripe for full-blown thunderstorms. Forecasters sometimes use the term deep convection to refer to convection that rises to high levels, which usually means thunderstorms. The tremendous amount of energy associated with CB stems from the release of latent heat as condensation occurs with the growing cloud. Thunderstorms can occur any time of year, though they are more common during the spring and summer seasons. They can occur anywhere in the continental United States but are not common along the immediate west coast, where an average of only about one per year occurs. During the summer months, the desert Southwest, extending northeastward into the Rocky Mountains and adjacent Great Plains, experiences an average of 30 to 40 thunderstorms annually. Additionally, in the southeastern United States, especially Florida, between 30 and 50 thunderstorms occur in an average year. Thunderstorms in the cool seasons usually occur in conjunction with some forcing mechanism, such as a fast-moving cold front or a strong upper-level trough. Figure 9.15, the life cycle of an air mass or ordinary thunderstorm consists of three main stages: cumulus, mature, and dissipating. The term ordinary describes the type of thunderstorm consisting of a single CB, since other types of thunderstorms, described below, can occur in a uniform large-scale air mass. The entire life cycle takes on the order of an hour, though remnant cloud from the dissipated CB can last substantially longer. The cumulus stage is characterized by a cumulus growing to a towering cumulus, Cu, or cumulus congestus. During this stage, most of the air within the cloud is going up. The size of the updraft increases, while the cloud base broadens to a few miles in diameter. Since the cloud has increased in size, the strong updraft in the middle of the cloud is not susceptible to entrainment of drier air from the outside. Often, other smaller cumulus in the vicinity of the Cu are suppressed by general downward motion around the cloud. Towards the end of the cumulus stage, downdrafts and precipitation begin to form within the cloud. On some days, small cumulus can be around for hours before Cu form, while on other days, the air is so unstable that almost as soon as any cumulus form, they become Cu. Figure 9.16, as the evolution of the thunderstorm continues, it reaches its mature stage. By this time, downdrafts reach the ground and spread out in what are known as downbursts or microbursts. These often lead to strong and sometimes damaging surface winds. Gliders should not be flown or exposed to microbursts and the associated wind shears. While increased headwinds can momentarily improve performance, the distance from the landing area may be increased beyond the capabilities of the glider. Attempting to launch with possible wind shears can result in fatal consequences. Note, launching of a glider either behind a towplane or ground launch is risky. Given the size of wind shears, the towplane could be in a tailwind situation while the glider is in a headwind situation. With the likely outcome of that combination of factors, and the hazards of ground handling, operations in such conditions must be severely discouraged. Pilots need to watch apparently dissipating thunderstorms closely for new dark, firm bases that indicate a new cell forming. In addition, outflow from one CB may flow several miles before encountering an area where the air is primed for lifting, given an extra boost. The relatively cool air in the outflow can provide that boost, leading to a CB, which is nearby but not connected to the original CB. Lifted index: the Li is determined by subtracting the temperature of a parcel that has been lifted to 500 MB from the temperature of the ambient air. This index does not give the likelihood of thunderstorm occurrence, rather, it gives an indication of thunderstorm severity if one does occur. In Figure 9.17, an Li of -5 indicates moderately severe thunderstorms if they develop. K-index. The key is used to determine the probability of thunderstorm occurrence and uses information about temperature and moisture at 3 levels. It is given by the equation key equals T850, T500, plus TD850, T700, TD700. Here, T stands for temperature, TD is the dew point, and 500, 700, or 850 indicates the level in MB. All values are obtained from a morning sounding. Using the following values from a morning sounding, key equals 16-9 plus 12, 6 to 0, equals 31. This indicates about a 60% probability that thunderstorms will occur. Figure 9.18 as discussed below, charts showing both the Lee and key for all the sounding sites in the continental United States are produced daily. Thunderstorms have several hazards, including turbulence, strong updrafts and downdrafts, strong shifting surface winds, hail, icing, poor visibility and/or low ceilings, lightning, and even tornadoes. Once a cloud has grown to be a CB, hazards are possible, whether or not there are obvious signs. Since thermal soaring weather can rapidly deteriorate into thunderstorm weather, recognition of each hazard is important. Knowledge of the many hazards may inspire the pilot to land and secure the glider when early signs of thunderstorm activity appear, the safest solution. Moderate turbulence is common within several miles of a thunderstorm, and it should be expected. Severe or even extreme turbulence, leading to possible structural failure, can occur anywhere within the thunderstorm itself. The inside of a thunderstorm is no place for glider pilots of any experience level. Outside of the storm, severe turbulence is common. One region of expected turbulence is near the surface gust front as cool outflow spreads from the storm. Violent updrafts can be followed a second or two later by violent downdrafts, with occasional side gusts adding to the excitement, not a pleasant proposition while in the landing pattern. At somewhat higher altitudes, but below the base of the CB, moderate to severe turbulence can also be found along the boundary between the cool outflow and warm air feeding the CB. Unpredictable smaller-scale turbulent gusts can occur anywhere near a thunderstorm, so recognizing and avoiding the gust front does not mean safety from severe turbulence. Large and strong updrafts and downdrafts accompany thunderstorms in the mature stage. Updrafts under the CB base feeding into the cloud can easily exceed 1000 fpm. Near the cloud base, the distance to the edge of the cloud can be deceptive. Trying to avoid being inhaled into the cloud by strong updrafts can be difficult. In the later cumulus and early mature stage, updrafts feeding the cloud can cover many square miles. As the storm enters its mature stage, strong downdrafts, called downbursts or microbursts, can be encountered, even without very heavy precipitation present. Downbursts can also cover many square miles with descending air of 2000 fpm or more. A pilot unlucky enough to fly under a forming downburst, which may not be visible, could encounter sink of 2000 or 3000 fpm, possibly greater in extreme cases. If such a downburst is encountered at pattern altitude, it can cut the normal time available to the pilot for planning the approach. For instance, a normal 3-minute pattern from 800 feet AGL to the ground happens in a mere 19 seconds in 2500 fpm sink. When a downburst or microburst hits the ground, the downdraft spreads out, leading to the strong surface winds, known as thunderstorm outflow. Typically, the winds strike quickly and give little warning of their approach. While soaring, pilots should keep a sharp lookout between the storm and the intended landing spot for signs of a wind shift. Blowing dust, smoke, or wind streaks on a lake indicating wind from the storm are clues that a gust front is rapidly approaching. Thunderstorm outflow winds are usually at speeds of 20 to 40 knots for a period of 5 to 10 minutes before diminishing. However, winds can easily exceed 60 knots, and in some cases, with a slow-moving thunderstorm, strong winds can last substantially longer. Although damaging outflow winds usually do not extend more than 5 or 10 miles from the CB, winds of 20 or 30 knots can extend 50 miles or more from large thunderstorms. Hail is possible with any thunderstorm and can exist as part of the main rain shaft. Hail can also occur many miles from the main rain shaft, especially under the thunderstorm anvil. Pea-sized hail usually does not damage a glider, but the large hail associated with a severe storm can dent metal gliders or damage the gel coat on composite gliders, whether on the ground or in the air. Icing is usually a problem only within a cloud, especially at levels where the outside temperature is approximately -10 degrees Celsius. Under these conditions, supercooled water droplets, water existing in a liquid state 0 degrees Celsius and below, can rapidly freeze upon contact with wings and other surfaces. At the beginning of the mature stage, early precipitation below cloud base may be difficult to see. At times, precipitation can even be falling through an updraft feeding the cloud. Snow, graupel, or ice pellets falling from the forming storm above can stick to the leading edge of the wing, causing degradation in performance. Rain on the wings can be a problem since some airfoils can be adversely affected by water. Poor visibility due to precipitation and possible low ceilings as the air below the thunderstorm is cooled is yet another concern. Even light or moderate precipitation can reduce visibility dramatically. Often, under a precipitating CB, there is no distinction between precipitation and actual cloud. Lightning in a thunderstorm occurs in cloud to cloud, in the case of other nearby storms, such as a multi-cell storm, or cloud to ground. Lightning strikes are completely unpredictable, and cloud-to-ground strikes are not limited to areas below the cloud. Some strikes emanate from the side of the CB and travel horizontally for miles before turning abruptly towards the ground. In-flight damage to gliders has included burned control cables and blown-off canopies. In some cases, strikes have caused little more than mild shock and cosmetic damage. On the other extreme, a composite training glider in Great Britain suffered a strike that caused complete destruction of one wing. Fortunately, both pilots parachuted to safety. In that case, the glider was 2 or 3 miles from the thunderstorm. Finally, ground launching, especially with a metal cable, anywhere near a thunderstorm should be avoided. Severe thunderstorms can sometimes spawn tornadoes, which are rapidly spinning vortices, generally a few hundred to a few thousand feet across. Winds can exceed 200 miles per hour. Tornadoes that do not reach the ground are called funnel clouds. By definition, tornadoes form from severe thunderstorms and should obviously be avoided on the ground or in the air. Weather for slope or ridge soaring refers to using updrafts produced by the mechanical lifting of air as it encounters the upwind slope of a hill, ridge, or mountain. Slope soaring requires 2 ingredients: elevated terrain and wind. Slope lift is the easiest lift source to visualize. When it encounters topography, wind is deflected horizontally, vertically, or in some combination of the two. Not all topography produces good slope lift. Individual or isolated hills do not produce slope lift because the wind tends to deflect around the hill, rather than over it. A somewhat broader hill with a windward face at least a mile or so long, might produce some slope lift, but the lift is confined to a small area. The best ridges for slope soaring are at least a few miles long. Slope lift can extend to a maximum of 2 or 3 times the ridge height. However, the pilot may be able to climb only to ridge height. As a general rule, the higher the ridge above the adjacent valley, the higher the glider pilot can climb. Ridges only 100 or 200 feet high can produce slope lift. The problem with very low ridges is maintaining safe maneuvering altitude, as well as sufficient altitude to land safely in the adjacent valley. Practically speaking, 500 to 1,000 feet above the adjacent valley is a minimum ridge height. Figure 9.19, in addition to a ridge being long and high enough, the windward slope needs to be steep enough as well. An ideal slope is on the order of 1 to 4. Shallower slopes do not create a vertical wind component strong enough to compensate for the glider's sink rate. Very steep, almost vertical slopes, on the other hand, may not be ideal either. Such slopes create slope lift, but can produce turbulent eddies along the lower slope or anywhere close to the ridge itself. In such cases, only the upper part of the slope may produce updrafts, although steeper slopes do allow a quick escape to the adjacent valley. Figure 9.20, a ridge upstream can block the wind flow, so that no low-level flow occurs upwind of an otherwise promising ridge, and no updraft. Additionally, if lee waves are produced by an upstream ridge or mountain, slope lift can be enhanced or destroyed, depending on the wavelength of the lee waves. Locally, the downdraft from a thermal just upwind of the ridge can cancel the slope lift for a short distance. The bottom line: never assume slope lift is present. Always have an alternative. Just as the flow is deflected upward on the windward side of a ridge, it is deflected downward on the lee side of a ridge. Figure 9.21, this downdraft can be alarmingly strong, up to 2000 fpm or more near a steep ridge with strong winds, see depiction A. Even in moderate winds, the downdraft near a ridge can be strong enough to make penetration of the upwind side of the ridge impossible. Flat-topped ridges also offer little refuge, since sink and turbulence can combine to make an upwind penetration impossible, see depiction B. Finally, an uneven upwind slope with ledges or steps requires extra caution since small-scale eddies, turbulence, and sink can form there, see depiction C. Three-dimensional effects are important as well. For instance, a ridge with cusps or bowls may produce better lift in upwind-facing bowls if the wind is at an angle from the ridge. However, sink may be encountered on the lee side of the bowl. If crossing ridges in windy conditions, always plan for heavy sink on the lee side and make sure an alternative is available. Figure 9.22, depending on the slope, wind speed should be 10 to 15 knots and blowing nearly perpendicular to the ridge. Wind directions up to 30 degrees or 40 degrees from perpendicular may still produce slope lift. Vertical wind shear is also a consideration. High ridges may have little or no wind along the lower slopes, but the upper parts of the ridge may be in wind strong enough to produce slope lift there. The area of best lift varies with height. Below the ridge crest, the best slope lift is found within a few hundred feet of the ridge, again depending on the slope and wind strength. As mentioned, very steep ridges require extra speed and caution since eddies and turbulence can form even on the upwind side. Above the ridge crest, the best lift usually is found further upwind from the ridge the higher one climbs. Figure 9.19, when the air is very stable, and the winds are sufficient but not too strong, slope lift can be very smooth, enabling safe soaring close to the terrain. If the air is not stable, thermals may flow up the slope. Depending on thermal strength and wind speed, the thermal may rise well above the ridge top, or it may drift into the lee downdraft and break apart. Downdrafts on the sides of thermals can easily cancel the slope lift. Extra speed and caution are required when the air is unstable, especially below the ridge crest near the terrain. The combination of unstable air and strong winds can make slope soaring unpleasant or even dangerous for the beginning glider pilot. Moisture must be considered. If air rising in the slope lift is moist and cools sufficiently, a so-called cap cloud may form. The cloud may form above the ridge, and if the air moistens more with time, the cloud slowly lowers onto the ridge and down the upwind slope, limiting the usable height of the slope lift. Since the updraft forms the cloud, it is very easy to climb into the cap cloud. Figure 9.23, a dangerous situation. Under certain conditions, a morning cap cloud may rise as the day warms, then slowly lower again as the day cools. Wave soaring weather where there is wind and stable air, there is the likelihood of waves in the atmosphere. Most of the waves that occur throughout the atmosphere are of no use to the glider pilot. However, mountains or ridges often produce waves downstream, the most powerful of which have lifted gliders to 49,000 feet. Indirect measurements show waves extending to heights around 100,000 feet. If the winds aloft are strong and widespread enough, mountain lee waves can extend the length of the mountain range. Pilots have achieved flights in mountain wave using 3 turn points of over 2,000 kilometers. Another type of wave useful to soaring pilots is generated by thermals, which were discussed in the previous section. A common analogy to help visualize waves created by mountains or ridges uses water flowing in a stream or small river. A submerged rock causes ripples, waves, in the water downstream, which slowly dampen out. This analogy is useful, but it is important to realize that the atmosphere is far more complex, with vertical shear of the wind and vertical variations in the stability profile. Wind blowing over a mountain does not always produce downstream waves. Mountain wave lift is fundamentally different from slope lift. Slope soaring occurs on the upwind side of a ridge or mountain, while mountain wave soaring occurs on the downwind side. Mountain wave lift sometimes tilts upwind with height. Therefore, at times near the top of the wave, the glider pilot may be almost directly over the mountain or ridge that produced the wave. The entire mountain wave system is also more complex than the comparatively simple slope soaring scenario. Mechanism for wave formation: waves form in stable air when a parcel is vertically displaced, and then oscillates up and down as it tries to return to its original level, illustrated in Figure 9.24. In the first frame, the dry parcel is at rest at its equilibrium level. In the second frame, the parcel is displaced upward along the dowel, where it is cooler than the surrounding air. The parcel accelerates downward toward its equilibrium level, but it overshoots the level due to momentum and keeps going down. The third frame shows that the parcel is now warmer than the surrounding air, and starts upward again. The process continues with the motion damping out. The number of oscillations depends on the initial parcel displacement and the stability of the air. In the lower part of the figure, wind has been added, illustrating the wave pattern that the parcel makes as it oscillates vertically. If there were no wind, a vertically displaced parcel would just oscillate up and down, while slowly damping, at one spot over the ground, much like a spring. Figure 9.24. The lower part of Figure 9.24 also illustrates 2 important features of any wave. The wavelength is the horizontal distance between 2 adjacent wave crests. Typical mountain wavelengths vary considerably, between 2 and 20 miles. The amplitude is half the vertical distance between the trough and crest of the wave. Amplitude varies with altitude and is smallest near the surface and at upper levels. As a note, mountain lee waves are sometimes simply referred to as mountain waves, lee waves, and sometimes, standing waves. In the case of mountain waves, it is the airflow over the mountain that displaces a parcel from its equilibrium level. This leads to a 2-dimensional conceptual model, which is derived from the experience of many glider pilots plus post-flight analysis of the weather conditions. Figure 9.25 illustrates a mountain with wind and temperature profiles. Note the increase in wind speed, blowing from left to right, with altitude and a stable layer near mountaintop with less stable air above and below. As the air flows over the mountain, it descends the lee slope, below its equilibrium level if the air is stable, and sets up a series of oscillations downstream. The wave flow itself usually is incredibly smooth. Beneath the smooth wave flow is what is known as a low-level turbulence zone, with an embedded rotor circulation under each crest. Turbulence, especially within the individual rotors, is usually moderate to severe, and can occasionally become extreme. Figure 925, this conceptual model is often quite useful and representative of real mountain waves, but many exceptions exist. For instance, variations to the conceptual model occur when the topography has many complex, three-dimensional features, such as individual higher peak, large ridges, or spurs at right angles to the main range. Variations can occur when a north-south range curves to become oriented northeast-southwest. In addition, numerous variations of the wind and stability profiles are possible. Turbulence associated with lee waves deserves respect. Low-level turbulence can range from unpleasant to dangerous. Glider pilots refer to any turbulence under the smooth wave flow above as rotor. The nature of rotor turbulence varies from location to location as well as with different weather regimes. At times, rotor turbulence is widespread and fairly uniform, that is, it is equally rough everywhere below the smooth wave flow. At other times, uniformly moderate turbulence is found, with severe turbulence under wave crests. On occasion, no discernible turbulence is noted except for moderate or severe turbulence within a small-scale rotor under the wave crest. Typically, the worst turbulence is found on the leading edge of the primary rotor. Unfortunately, the type and intensity of rotor turbulence are difficult to predict. However, the general rule of thumb is that higher amplitude lee waves tend to have stronger rotor turbulence. Clouds associated with the mountain wave system are also indicated in Figure 925. A cap cloud flowing over the mountain tends to dissipate as the air force down the mountain slope warms and dries. The first, or primary, wave crest features a roll or rotor cloud with one or more lenticulars, or lennies, using glider slang, above. Wave harmonics farther downstream, secondary, tertiary, etc. may also have lenticulars and or rotor clouds. If the wave reaches high enough altitudes, lenticulars may form at cirrus levels as well. It is important to note that the presence of clouds depends on the amount of moisture at various levels. The entire mountain wave system can form in completely dry conditions with no clouds at all. If only lower level moisture exists, only a cap cloud and rotor clouds may be seen with no lenticulars above, as in Figure 926a. On other days, only mid-level or upper-level lenticulars are seen with no rotor clouds beneath them. When low and mid-levels are very moist, a deep rotor cloud may form, with lenticulars right on top of the rotor cloud, with no clear air between the two cloud forms. In wet climates, the somewhat more moist air can advect, meaning to convey horizontally by advection, such that the gap between the cap cloud and primary rotor closes completely, stranding the glider on top of the clouds, as in Figure 926b. Caution is required when soaring above clouds in very moist conditions. Suitable terrain is required for mountain wave soaring. Even relatively low ridges of 1,000 feet or less vertical relief can produce lee waves. Wave amplitude depends partly on topography, shape and size. The shape of the lee slope, rather than the upwind slope, is important. Very shallow lee slopes are not conducive to producing waves of sufficient amplitude to support a glider. A resonance exists between the topography width and lee wavelength that is difficult to predict. One particular mountain height, width, and lee slope is not optimum under all weather conditions. Different wind and stability profiles favor different topography profiles. Hence, there is no substitute for experience at a particular soaring site when predicting wave soaring conditions. Uniform height of the mountaintops along the range is also conducive to better organized waves. The weather requirements for wave soaring include sufficient wind and a proper stability profile. Wind speed should be at least 15 to 20 knots at mountaintop level with increasing winds above. The wind direction should be within about 30 degrees perpendicular to the ridge or mountain range. The requirement of a stable layer near mountaintop level is more qualitative. A sounding showing a dour, or nearly so, near the mountaintop would not likely produce lee waves even with adequate winds. A well-defined inversion at or near the mountaintop with less stable air above is best. Weaker lee waves can form without much increase in wind speed with height, but an actual decrease in wind speed with height usually caps the wave at that level. When winds decrease dramatically with height, for instance, from 30 to 10 knots over 2 or 3,000 feet, turbulence is common at the top of the wave. On some occasions, the flow at mountain level may be sufficient for wave, but then begins to decrease with altitude just above the mountain, leading to a phenomenon called rotor streaming. In this case, the air downstream of the mountain breaks up and becomes turbulent, similar to rotor, with no lee waves above. Lee waves experience diurnal effects, especially in the spring, summer, and fall. Height of the topography also influences diurnal effects. For smaller topography, as morning leads to afternoon and the air becomes unstable to heights exceeding the wave-producing topography, lee waves tend to disappear. On occasion, the lee wave still exists but more height is needed to reach the smooth wave lift. Toward evening, as thermals again die down and the air stabilizes, lee waves may again form. During the cooler season, when the air remains stable all day, lee waves are often present all day, as long as the winds aloft continue. The daytime dissipation of lee waves is not as notable for large mountains. For instance, during the 1950 Sierra Wave Project, see www.soaringmuseum.org, it was found that the wave amplitude reached a maximum in mid to late afternoon, when convective heating was a maximum. Rotor turbulence also increased dramatically at that time. Topography upwind of the wave-producing range can also create problems, as illustrated in Figure 927. In the first case, Figure 927A, referred to as destructive interference, the wavelength of the wave from the first range is out of phase with the distance between the ranges. Lee waves do not form downwind of the second range, despite winds and stability aloft being favorable. In the second case, Figure 927B, referred to as constructive interference, the ranges are in phase, and the lee wave from the second range has a larger amplitude than it might otherwise. Wave flight is a unique soaring experience and requires planning, equipment and Federal Aviation Administration, FAA, notification for the flight. The Soaring Society of America, SSA, awards and badges offers soaring pilots Lenny Awards for completing and documenting a wave flight. Figure 928, isolated small hills or conical mountains do not form classic lee waves. In some cases, they do form waves emanating at an angle to the wind flow similar to water waves created by the wake of a ship. A single peak may require only a mile or two in the dimension perpendicular to the wind for high-amplitude lee waves to form, though the wave lift is confined to a relatively small area in these cases. Lift due to convergence. Convergence lift is most easily imagined when easterly and westerly winds meet. When two opposing air masses meet, air is pushed aloft by the two opposing winds. Air does not need to meet head-on to go up, however. Wherever air piles up, it leads to convergence and rising air. One type of convergence line commonly found near coastal areas is the so-called sea breeze front. Inland areas heat during the day, while the adjacent sea maintains about the same temperature. Inland heating leads to lower pressure, drawing in cooler sea air. As the cooler air moves inland, it behaves like a miniature shallow cold front, and lift forms along a convergence line. Sometimes consistent lift can be found along the sea breeze front, while at other times it acts as a focus for a line of thermals. If the inland air is quite unstable, this sea breeze front can act as a focus for a line of thunderstorms. Additionally, since the air on the coast side of the sea breeze front is rather cool, passage of the front can spell the end of thermal soaring for the day. Sea air often has a higher dew point than drier inland air. As shown in Figure 929, a curtain cloud sometimes forms, marking the area of strongest lift. Due to the mixing of different air along the sea breeze front, at times the lift can be quite turbulent. At other times, weak and fairly smooth lift is found. Several factors influence the sea breeze front character, for example, turbulence strength and speed of inland penetration, including the degree of inland heating and the land/sea temperature difference. For instance, if the land/sea temperature difference at sunrise is small and overcast cirrus clouds prevent much heating, only a weak sea breeze front, if any, forms. Another factor is the synoptic wind flow. A weak synoptic onshore flow may cause quicker inland penetration of the sea breeze front, while a strong onshore flow may prevent the sea breeze front from developing at all. On the other hand, moderate offshore flow generally prevents any inland penetration of the sea breeze front. If the sea breeze front is well defined and marked by a curtain cloud, the pilot can fly straight along the line in fairly steady lift. A weaker convergence line that is not well defined often produces more lift than sink, and the pilot must fly slower in lift and faster in sink. Soaring pilots must be aware that convergence zone lift can be turbulent, especially if the colder and warmer air is mixing, and be prepared that flying the thermals may be difficult at times. Convergence can also occur along and around mountains or ridges. In Figure 930A, flow is deflected around a ridgeline and meets as a convergence line on the lee side of the ridge. The line may be marked by cumulus or a boundary with a sharp visibility contrast. The latter occurs if the air coming around one end of the ridge flows past a polluted urban area, such as in the Lake Elsinore soaring area in Southern California. In very complex terrain, with ridges or ranges oriented at different angles to one another, or with passes between high peaks, small-scale convergence zones can be found in adjacent valleys, depending on wind strength and direction. Figure 930b illustrates a smaller scale convergence line flowing around a single hill or peak and forming a line of lift stretching downwind from the peak. Convergence can also form along the top of a ridgeline or mountain range. In Figure 931, drier synoptic scale wind flows up the left side of the mountain, while a more moist valley breeze flows up the right side of the slope. The two flows meet at the mountain top and form lift along the entire range. If clouds are present, the air from the moist side condenses first, often forming one cloud with a well-defined step, marking the convergence zone. For this scenario, the better lift conditions will be found on the west side where the air is drier rather than the east side where clouds are more likely to form. As a final example, toward evening in mountainous terrain and as heating daytime abates, a cool adiabatic, or drainage, wind flows down the slopes. The flow down the slope converges with air in the adjacent valley to form an area of weak lift. Sometimes the convergence is not strong enough for general lifting, but acts as a trigger for the last thermal of the day. In narrow valleys, flow down the slope from both sides of the valley can converge and cause weak lift. Figure 932, many local sites in either flat or mountainous terrain have lines or zones of lift that are likely to be caused or enhanced by convergence. Chapter 10, Soaring Techniques, covers locating and using convergence. Obtaining weather information. One of the most important aspects of flight planning is obtaining reliable weather information. Fortunately, pilots have several outlets to receive reliable weather reports and forecasts to help them determine if a proposed flight can be completed safely. For visual flight rules, VFR, flights, federal regulations require pilots to gather weather reports and forecasts only if they plan to depart the airport vicinity. Nevertheless, it is always a good idea to be familiar with the current and expect weather anytime a flight is planned. Pre-flight weather information sources include Automated Flight Service Stations, AFSS, and National Weather Service, NWS, telephone briefers, the Direct User Access Terminal System, DUITS, and the Internet. In addition, a multitude of commercial vendors provide custom services. For complete details regarding available weather services and products, refer to the current version of the FAA Advisory Circular, AC 00-45, Aviation Weather Services, and in the Pilot's Handbook of Aeronautical Knowledge, Chapter 12, Aviation Weather Services. Pre-flight weather briefing. Oftentimes, in order to obtain a pre-flight weather briefing, certain background information must be given to the weather specialist. Type of flight plan, whether flying VFR, visual flight rules, or IFR, instrument flight rules, aircraft registration or pilot's name, aircraft type, departure airport, route of flight, destination, flight altitudes, estimated time of departure, ETD, and estimated time on route, ETE. Operators of airports, glider ports, or fixed base operators, FBO, may obtain current reports and forecasts from the AFSS or NWS at various times throughout the day and post them on a bulletin board for easy reference. Weather briefers do not actually predict the weather, they simply translate and interpret weather reports and forecasts within the vicinity of the airport, route of flight, or the destination airport if the flight is across country. A pilot may request one of four types of briefings: standard, abbreviated, soaring, figure 933, or Outlook. Weather-related information. Weather-related information can be found on the internet, including sites directed toward aviation. These sites can be found using a variety of internet search engines. It is important to verify the timeliness and source of the weather information provided by the internet sites to ensure the information is up to date and accurate. Pilots should exercise caution when accessing weather information on the internet, especially if the information cannot be verified. Other sources of accurate weather information are the NWS website located at www.nws.noaa.gov, the NOAA site at http://aviationweather.gov/ad/meters/ and Dr. Jack's regional forecasts at http://www.drjack.info/blip/ruck. Interpreting weather charts, reports, and forecasts. Knowing how and where to gather weather information is important, but the ability to interpret and understand the information requires additional knowledge and practice. Weather charts and reports are merely records of observed atmospheric conditions at certain locations at specific times. Trained observers using electronic instruments, computers, and personal observations produce the weather products necessary for pilots to determine if a flight can be conducted safely. This same information can be used by soaring pilots to determine where they can find lift, and how long the lift is usable for soaring flight. Graphic weather charts. Reports of observed weather are graphically depicted in a number of weather products. Among them are the Surface Analysis Chart, Radar Summary Chart, Weather Depiction Chart, Winds and Temperature Aloft Chart, and the Composite Moisture Stability Chart. For detailed information about the surface analysis chart, weather depiction charts, and radar summary chart, refer to the Pilot's Handbook of Aeronautical Knowledge and Advisory Circular 0045G, Aviation Weather Services. Winds and Temperatures Aloft Forecast. The Winds and Temperatures Aloft Forecast, FB, is a 12-hour product that is issued at 0000Z and 1200Z daily. Figure 934, it is used primarily to determine expected wind direction and velocity, and temperatures for the altitude of a planned cross-country flight. The forecast contains 9 columns that correspond to forecast levels 3,000, 6,000, 9,000, 12,000, 18,000, 24,000, 30,000, 34,000, and 39,000 feet MSL. Soaring pilots planning to attempt proficiency for altitude should be aware that the levels below 18,000 feet are based on local altimeter settings. Above 18,000 feet, flight levels are based on standard altimeter setting of 29.92 Hg. For example, 19,000 feet is FL 190. Wind direction is from true north. No winds are forecast within 1,500 feet of station elevation. Also, no temperatures are forecast for the 3,000-foot level or for any level within 2,500 feet of station elevation. Temperature is in whole degrees Celsius and assumed to be negative above 24,000 feet. Figure 934 shows an example winds aloft message as well as how to decode it. Note, the winds aloft forecasts were formerly known as FD. Composite Moisture Stability Chart. The Composite Moisture Stability Chart is a 4-panel chart, which depicts stability, precipitable water, freezing level, and average relative humidity. It is a computer-generated chart derived from upper air observation data and is available twice daily with a valid time of 0000Z and 1200Z. This chart is useful for determining the characteristics of a particular weather system with regard to atmospheric stability, moisture content, and possible aviation hazards, such as thunderstorms and icing. Figure 935, for the purpose of soaring flight, the stability panel located in the upper left corner of the chart, Figure 935 Panel A, can be useful when obtaining weather as it outlines areas of stable and unstable air. The numbers on this panel resemble fractions. The top number is the lifted index Li and the lower number is the K index He. Figure 936, the Li is the difference between the temperature of a parcel of air being lifted from the surface to the 500 MB level, approximately 18,000 feet MSL, and the actual temperature at the 500 MB level. If the number is positive, the air is considered stable. For example, a lifted index of +8 is very stable, and the likelihood of severe thunderstorms is weak. Conversely, an index of -6 or less is considered very unstable, and severe thunderstorms are likely to occur. However, the instability may give rise to favorable soaring conditions. A 0 index is neutrally stable. Figure 937, the chart in Figure 937 shows relative instability in 2 ways. First, the station circle is darkened when the lift index is 0 or less. Second, solid lines are used to delineate areas that have an index of +4 or less at intervals of 4, +4, 0, -4, -8. The stability panel is an important pre-flight planning tool because the relative stability of an air mass is indicative of the type of clouds that can be found in a given area. For example, if the air mass is stable, a pilot can expect smooth air and, given sufficient moisture, steady precipitation. On the other hand, if the air mass is unstable, convective turbulence and showery precipitation can be expected. The K index indicates whether the conditions are favorable for air mass thunderstorms. The K index is based on temperature, low-level moisture, and saturation. A K index of 15 or less would be forecast as a 0% probability for air mass thunderstorms, and an index of 40 or more would be forecast as 100% probability. Figure 938, caution should be exercised if the K index is high, indicating moisture is sufficient for storm development. Although the lifting index may be very negative and good for soaring, too much moisture can make good soaring conditions very dangerous once the storms develop. A very negative Li with high Ki may mean a better day to soar close to the glider port, whereas very negative Li and low Ki values make for clear soaring conditions in general.